Good morning, distinguished teaching team. We are group 2 and we have 4 members in our group. So our group focus is on efficient power converter, especially for buck boost converter. According to our research, we have found that the main problem of the converter is from its loss due to heat and switching loss. So from that, we divided our objective into two parts. First, simulation, and second, the model. For simulation, we want to design high-efficiency DC-DC converter by using the SiC and GaN MOSFETs in order to higher the efficiency of the converters to more than 85% in order to support the overall of sustainable energy. So for our physical model, we want to build a model that reduces the power loss. According to our initial plan, we have divided our work into 4 important parts, which is done consequently by each member of our team that I will explain more in next slides. Regarding to our initial plan, we have achieved the main goal of our projects, which is to finish the simulation part. That is first, Mickey, our member, she initially finished the construction of the main circuits with PWM divider. And also Jeff, he completed the implementing, tuning, the voltage and current sampling. Next, Kofi finished building a PI controller and integrate protections. For myself, I finished conducting the performance and efficiency tests. Together with our simulation work, we have proposed 3 solutions, which is hybrid architecture by using GaN for high frequency switching and using SiC for high voltage and high current handling, and also bidirectional energy flow between PV battery and the load. For circuit construction, we have referred to the source which is reliable from power electronic and application unit. We have chosen the buck boost converter from the PV energy system.
Let's get started. First, let's look at these 8 main formulas. They are very important in circuit design. For example, the output voltage formula can define the exact output voltage. There are also some formulas specifically used to determine circuit parameters, such as inductor and capacitor parameters, which are directly related to the circuit's performance and form the basis of the entire design calculation. Next, the technical design. I've divided into 4 tasks. I'm in charge of the buck boost converter simulation, which consists of input PWM driver, MOSFET, inductor, and capacitor. The PWM driver controls the switching of the MOSFET, and the inductor and capacitor work together to achieve voltage conversion, which is the foundation for the entire circuit's operation. Then, the feedback sensing part, which uses methods like voltage divider. It accurately collects the output voltage and current signals through voltage divider circuits and others. After RC filtering, these clean and accurate signals are sent to the controller, allowing the controller to adjust the circuit status in real time based on this information. Next, the control and testing. We mainly focus on buck conversion. The control part uses a PID controller with 5 voltage reference, which makes price adjustments based on feedback signals. The goal is to achieve an efficiency of over 85% through these processes. Ensure that the buck boost converter works efficiently and stably. There are the ripple waves of the inductor and the capacitors. They are indicating a significant effect in suppressing current ripple and in a strong ability to suppress output voltage ripple, and the overall circuit stability is good.
Our protection design begins with a PID, which has a current sensing circuit that monitors either the inductor current or the output current. This signal is fed into two comparators, which are part of this PID, to evaluate overload conditions. When comparator 1 detects a current above 3 amps, the clamp logic limits the duty cycle. This clamp down action instantly reduces the pulse width modulation duty ratio to prevent current overshoot and protect the MOSFET from stress. If the current continues to rise and triggers comparator 2, a shutdown latch is activated, forcing the pulse width modulation signal to 0 and accelerating the converter. The latch can only be cleared through manual reset, ensuring the fault is verified before restarting. Together, the clamp down and shutdown mechanisms form a two-stage protection hierarchy that preserves converter stability and prevents catastrophic failure during fault or overload events. Our simulation results confirm the effectiveness of these control and protection systems. Ripple and dynamic response, as can be found here, remain minimal across all load conditions, proving that the clamp logic maintains smooth operations during transient. In terms of performance, the converter delivers 5 volts at 1.4 amps output from 12 volts at 0.65 amps input, achieving nearly 89.7% efficiency. This achieves our target of above 85%. The converter efficiency peaks at 89.7% and remains above 85% across all different loads, as it will be discussed further by Jeff. Additionally, the hybrid architecture reduces thermal stress, keeping the device temperature low under full load operations. This shows that our design successfully balances stability, safety, and efficiency.
The current keeps a very stable output even when the load changes suddenly. Low ripple, fast settling, no overshoot. Our peak efficiency is about 89.7% and we stay above roughly 85% across different loads. Also, even under heavy loads, the temperature stays low, which means less thermal stress and better reliability. Higher efficiency means less wasted energy and less cooling handwear. The design can rotate energy flexibly between, for example, solar, a battery, and the load, and it can be built as a compact, scalable module for renewable systems. Because the design is modular, it can be used in both residential and industrial settings. Its performance is competitive with model converters. This maps to real markets: EV power electronics, solar pass storage, and microgrids. Finally, we have validated the design in simulation. Our next step is hardware prototyping and adding MPPT so the system can directly connect to the real renewable sources. The goal is to turn this into something deployable in sustainable energy systems, not just a simulation model. That's all.